Hey all, we're going to take a minute here to introduce you to our next unit on energy. This video is going to take you through the different types of energy that you're going to come across, how to spot them, and then how to see the transfer between the different forms. The first energy we're going to talk about is stored energy or potential energy. There's a few different types of potential energy, so you're going to want to be specific as to how the energy is being stored. Is it being stored due to its height? Is it being stored due to a stretched or compressed spring? And so on. The first one we're going to look at is chemical energy. Chemical energy is energy that is stored within chemical bonds. We're going to see this when it comes to an object needing some sort of a fuel or a food in order to function. For example, our bodies need food. Without food, our body does not create the heat that it gives off. Our body will not move the way that it's supposed to, right? Anybody that's ever tried to work out after not eating for any amount of time will notice that the workout's just not going to be as good, right? Our body needs that fuel, that food, just like a car, right? Your average car needs gasoline in order to run, right? Your TV remote control needs batteries in order to work, right? That's a fuel that causes that all of that to work. That's an energy source. The next one is electrical energy, energy that is stored within electrical fields. Typically, in order to spot this, we're going to look for wires, right? Electricity needs wires to run through. So when we see wires, we know that there's electrical energy. The next one is elastic spring energy or spring potential energy. This is energy that is stored when an object is stretched or compressed. Think about a spring. A spring, when we stretch it, it springs back, it comes back to its original form. When we compress it, it comes back to its original form, right? A tennis ball, why does a tennis ball bounce when, say, like a billiard ball wouldn't, right? A tennis ball bounces because it compresses into, it kind of, the part that hits the ground flattens out and it springs back and it pushes it back, right? So this is why it bounces more than another object would, right? So anytime we have any sort of a stretch or a compression, that's when we know we're dealing with stored elastic energy, spring energy. Gravitational potential energy is energy that is due to height, right? We have gravitational potential energy because we are off the ground. And if something were to happen, say we fall or you let go of an object, it will fall towards the earth. What we know about this, or what's kind of interesting about this, is we get to determine how much energy or potential energy an object has based on where it could possibly fall to. We'll get to that in just a moment. But gravitational potential energy is energy that is due to height. The next energy that's easy to spot is kinetic. Kinetic energy is energy that is due to motion or velocity. Anytime an object is moving, it has kinetic energy. Nuclear energy is another type of a potential energy. It's energy that is stored within the nucleus of an atom. This is one of the strongest energies, right? If you think about the two types of nuclear reactions that are out there, the fission and the fusion reactions, both of them extremely, extremely powerful, right? Think about what happens when we split an atom, right? We split an atom and we get nuclear power plants, we get atomic bombs, we get things like that. Or even more potential energy is when we combine energy, the fusion energy, right? We have fusion energy, the power of the sun, right? Combining two nuclei to make one bigger nucleus, right? Those are nuclear energies. The next type of energies we're going to classify as one big thing. We're going to break it down right now so that you can see them and how to identify them. But when we work problems, we're going to just classify them all as dissipated energy. However, it's important to be able to recognize when these energies are there, right? And the different types of them. The first one is light energy, right? We see it, it's light, it gives off light. That's a dissipated energy. That's energy that goes off into the environment or off into the surroundings, and we don't get back to our object or whatever it is we're measuring, right? Lead energy is energy that's going to leave. Sound energy is another sort of dissipated energy, right? We hear it. When we hear something, that's sound that is happening, that is coming from a vibration, right? That vibration causes air particles to move, and that moves the particle next to it, which moves the particle next to it, which moves it all the way from whatever the source of the sound is to our eardrum. Then that vibrates our eardrum, which sends a signal to our brain, right? All of that is energy. Sound energy is another form of a dissipated energy. It's an energy that is not going to, come back into our object. It's dissipated, it's gone, it's moved off out into the surroundings. Heat or thermal energy is another type of dissipated energy. Lastly, we've got deformation energy. That is energy that causes an object to deform that's not going to come back. And this is not like a spring energy where like the tennis ball deforms and then it comes back. This would be more like a clay ball that hits the ground, flattens out on one side, and then stays that way, right? That energy that it took to change the shape of the clay ball is a deformation type of energy. One of the things that we know about energy is that energy cannot be created or destroyed. Much like momentum, energy is a conservative property, right? However, as much as it cannot be created or destroyed, we know, think about just kinetic energy. An object can be moving, then it can be not moving, right? So it appears as though it gained energy. However, that kinetic energy came from another type of energy. Either you gave it a push, which means you turned your chemical energy into the kinetic energy of the ball. Or it was dropped, meaning we're turning the potential energy into the kinetic energy of an object. Right? Conservation of energy just means that energy is going to transfer from one form into the next. Okay? What I want to do is I'm going to add a page into this, just so that we can kind of go through some of these things, right? So first of all, when we're dealing with energy, we're going to break it down into a couple of different categories. We've got our mechanical energy. And then we've got our non-mechanical energies. Our mechanical energies are then broken down into two forms: potential energy and kinetic. Our non-mechanical energies are our dissipated energies. What we know is our energy can form and can flow from one form into the next. Let me give you an example. If we take a ball and we were to drop it off of the edge of a cliff, when we're at the top of the cliff, right, we have all of this gravitational potential energy. Gravitational energy is energy that is based on height. right? How far we are from a height of 0. The great thing about it is we get to determine what our height of 0 is, right? And we'll get to that in just a moment. When I drop this ball off of the cliff, it's going to move downward. As it moves downward, its velocity is going to go up. Well, if you remember, velocity is related to kinetic energy. So if the velocity goes up, the kinetic energy goes up. Well, gravitational energy is based on height. So as it goes down, the gravitational energy goes down, right? So we don't have this. We're not gaining energy. We're just transferring from one form to the next. So now, I had said earlier, a couple seconds ago, that we get to determine what our height is, what our 0 height is, right? Typically, right, we would say, well, the ground is our height of 0, because how much potential energy we have is based on how far we are from what we call a height of 0. And let me give you an example of this. Imagine being out in Las Vegas, right? Big, beautiful, large hotels out in Las Vegas, and you're up on the 40th floor of one, right? And if you're up on the 40th floor of a hotel, this is going to be a really, really, really bad drawing, right? 40th floor, you're about 400 feet up, right? And on that hotel, or in that hotel room, is a bed. You fall off of the bed. You literally can tell people that you fell from 402 feet and survived. Because you did. You were 402 feet up. However, does it really make a whole lot of sense if you were to fall out of the bed to make down here your height of 0? You can. It will work for you, and you can fall from 402 to 400. However, it's easier for us to just say, you know what? I fell 2 feet. Right? And you'll see when we get into the equations and how to calculate things, you'll see why that's easier. But it makes the most sense. It makes the most sense to figure wherever the lowest point that we can get to, make that your height of 0. It doesn't always have to be the ground. It doesn't make sense. If I'm in a hotel room 400 feet up, it doesn't make sense to make the ground my height of 0, because I'm not going to get there barring some crazy disaster, right? I'm going to make my lowest point a height of 0. Another example of that would be, say, like a pendulum, right? A pendulum is going to swing back and forth, and as it does, it's going to pass through this height right here. Well, I don't need to make the ground my height of 0. I'm going to make that my height of 0, right? So that's one of the things as far as a gravitational potential. One of the makes it a little easier for us. But let's go back to some of that energy transfer. We're going to add a page here. Let's go back to some of those ideas of an energy transfer. Take example, turning on a flashlight. This is my very bad flashlight. In the flashlight, there's a battery. Battery has some wires, and it connects to the bulb, and we get light that comes out of it. Okay? Think about what happens. Inside the battery, we have a chemical energy. That energy from the battery moves electrons that are in the wires, which means that chemical energy transfers into electrical. Yep, I can't spell. That electrical energy gets to the light bulb, where it turns into both light and heat. Right? That's what we're talking about when we talk about energy transfer and energy flow. Right? Another example of this, and this is a good one for right now. You know, right now we're in winter and it's really, really, really cold outside. In the summer, you guys have probably noticed, you park your car outside for a little while and you go and get inside and it's, you know, oh my God, it's so hot inside my car. Roll down the windows, let it air out for a little while. Why? Why is it so much hotter inside your car, right? The average person would say, well, there's no breeze inside the car, so the heat just gets trapped. It's partially right. The heat does get trapped, but it's not because there's not breeze. Think about what happens inside your car, right? We'll draw your car here. Okay, and in the car, you got your seats, which is probably, because most cars are, black, dark gray, some sort of a dark color. Okay, now, cars have this amazing invention that allows light to transfer through, known as windows. And this sunlight shines through these windows and hits the interior of your car. Now, one of the things that maybe you do or do not know about light and color is we see color because that's the color of the light, that's the wavelength of the light that gets reflected. Well, when we see something that's black, black is the absence of light, which means it's absorbing all of the light and not reflecting any of it back. Light's an energy, which means it can't just disappear. But what happens? Well, anybody that's ever been walking outside on a hot day with bare feet and then walked across somebody's driveway realizing how hot that is knows what happens. That light turns into heat. However, windows, the purpose of them is to allow light to transfer through, but not to allow heat, which means this heat that hits the window, just gets reflected back in. So you got all of this light coming in, turning into heat, and then all of this heat that can't escape, right? And that's why the temperature in our car goes up. Right, so just kind of an everyday idea of how energy is transferred. Now, a little bit of a physics nerd tip here. Right now it's extremely cold outside because we're in winter, and the reason that happens is we're in the northern hemisphere and we're tilted away from the sun. So you'll notice that the sun in the sky right now, even at noon, is down towards the south. If you look towards the south, that's where you'll find the sun. If you want to keep your car just a little bit warmer for when you go into it, face your car to the south. If you can face your car to the south, that's where the sunlight will come in, and some of that light will come into the car, turn into heat, and get trapped inside. It's almost like leaving your heat on in the car while you're not in there. Right? So those are the types of energies. That's a little bit about energy transfer. If you have any questions, please reach out to myself, Mrs. Fine Ice, or Mrs. Colder. Otherwise, enjoy the rest of your day.